here I don't need power. Yes. Okay. I don't know if I don't. Maybe we do the taker. Okay. In the meantime, I can thank the faculty or the university for inviting me to be in Poland. And being in Poland is a little bit tricky because you have to direct your questions to both the audience and in a way that everybody would be happy in the sense that it's a good show. And so, first thing, maybe I have to say a few words. What is the purpose of this exercise? Many people think that, particularly students, that the idea here is to judge the scientific contribution, the scientific work of the respondent. That's part of the story. The main part of the story is that to see the respondent has experience called post-academic, which means education, research education. Research education means that he should be able to be an independent flyer in the research world. That means that you are capable of being putting yourself in a new area, reading what's all about, get the state of the art, critically read what other people are doing, critically design or innovatively design your research, define your research problem. Carry out the research, what you do, maybe find out what's the fault and what's missing, what should be done by others or by yourself. So it's not what you the ultimate outcome. It's maybe the way you come to that. That's the way you learn how to be a researcher. Because once you get your degree, then you're finished. You will have to rely by your own, and you cannot rely on your supervisor. So, and that's with that background, I'm going to ask the questions in the way that trying to see, you have to convince not myself, or the committee, that you are a flyer, free flyer in this research. So, and the committee, of course, is going to listen to what you are saying, and they're going to compare also check, or they have checked also your thesis, and they make a decision, of course, by their own. So, having said that, what I'm going to do is go through parts of the thesis, in particular those parts that I think I can contribute to the committee evaluation, and other parts I read because I know the committee is more expert on, how I can lead to that. And in the end, I do something which is at least I haven't seen that. I come back to your overheads. And we shall see if you are going to discuss your overheads. Okay. So, if we start in the very beginning, and this was also what you have shown in one of the last slide conclusion. Let me take it up, the last conclusion. You said the new solution code. You said the same thing in the abstract, and I put it in. Very much the same as you have the questions. 4 questions in the beginning of the thesis and if you look at the questions, you have number 1, new solution code. Here it says in the questions: is it possible to develop a new structural model? Unlike existing models. Has a really high level. Happy if you're writing on
the pattern of the I mean, it's possible to model the hash because I start with the
You don't have to write the equation, you can tell us why it works.
yeah,
Let's make the equation.
Yeah.
It works.
I only one up, so I define it. I say what is the difference between these different methods, and this is the continuity using the finite control variable, like the momentum also, but maybe we don't need to write them right now. But this is the finite volume, finite control volume method of solution. This is one of them. The other one is the differential technique, and this is the finite control volume technique. Two different techniques is possible. We wanted to know if we should solve this question by finite control volume method or infinitesimal control volume method. This is infinitesimal control volume method, and this is the finite control volume method. What is the difference? Every term in the finite control volume method is only per second. But in the differential analysis, every term is per second and per cubic meter. What does that mean? That if we wanted to model a digester, we wanted to know what is going to happen inside the digester. But this method, finite control volume method, stores the variables at the boundaries of the domain. If you have, for example, outlet here, inlet here, and atmosphere, is solved by finite control volume method. It solves the problem only at the boundaries of the domain. If we apply the momentum equation, then the other side would be sigma f, and this is the anchoring forces. Anchoring forces act only at the boundaries of the domain. So what we wanted to know, what is going to happen inside the digester. So, differential analysis, every term is per time and per meter. This means that it solves the variable inside the digester. This was the difference between differential analysis and control volume analysis. But we have also PSPR and PFR. PSPR, which is match mixing. These are the characteristics of the PSPR model. Match mixing. Uniform composition through the digester. uniform composition through the diagram. Variables are not a function of the position, or not function of position. This means that partial derivative goes to zero for when we use CFDR. Partial derivative goes to zero if you have then the exit stream as the same exit stream, as the same composition as inside the composition. This is the CFDR. But wait a second. Okay. So we do that.
I want to comment.
Okay. Yes.
Now, we have been talking quite a lot. First, I asked the question of
Yes,
as I said, we have alternative to this one. This is chemistry. That's what you show here. This is the mechanics. This is okay.
I can write it down.
So, if you could just make it a bit shorter. So this balance is zero, this is density, this is volume, and this is the area of this volume. So we take any control volume, any form, any shape, this is correct. In fact, it's just telling you that they take this part, density times volume is mass, and time rate of change in mass is equals to what's coming out from the wall.
Yeah,
It takes those sources.
But we can have sources also.
Yeah, but those sources. You want that's fine. This is correct for anyone.
Yes, yes. And control volume.
Any control volume.
Yes, this is control.
Surface of any volume. Usually by the boundaries of
Boundaries of
if they omega small enough, see this is valid for any omega, and you can use divergence theorem for that, and you can replace this one, integral divergence for rho u. Okay. Divergence of that is vector, divergence of that in the volume now. And if that is valid for any volume, so we satisfy this equation.
Yeah, yeah. This is the differential. This is the differential.
This is the same consequence of this.
Differential. Yes.
This is the consequence.
Yeah.
So if omega is getting smaller and smaller, this is the same. Because when you do your calculation, you do in fact go from here to here. Right. This is your final volume.
This is the final. This is infinitesimal control.
Yeah. This is the differential.
Infinitesimal control volume. This means
That's not control volume.
It is not control volume. No.
But here, you take the differential equation, and this one, and all the others.
Yes. These are the differential analysis. As differential analysis, we use the infinitesimal control volume. I mean that we divide we store the variables inside the digester. It means that we divide the when we want to solve this equation, partial differential equation, if we want to solve this partial differential equation, we have two possibilities. One is the exact solution, the next one is the approximate solution. Exact solution is applicable only for simple geometric problems, simple questions maybe. And I can write in past, maybe you don't have time to write in general form of the partial differential equation.
When you don't need to write.
No, I didn't want to write it, but I wanted to show that if you want to solve any partial differential equation, if you want to solve it partially, it depends on these coefficients. but this is different. And then, for example, these coefficients are B2, B2 minus minus 4, A, B. If it is larger or lower than 0 or equal to 0, we get different type of the differential equation, hyperbolic, for example, this is the hyperbolic equation. We derive from solution for analytical solution for the partial differential equation, but it's not general. There is no general solution for all the partial differential equation. That's why we use the approximate solution. What is the approximate solution? Approximate solution is finite volume method, finite difference method, and finite element method.
Wait a minute, you're repeating what you have in the book. We have seen that. Okay. Still, you are talking about things. Now, how do you show it's possible? Yeah, you're coming back.
Yeah.
You know all these things. Is it possible? How do you show it's possible?
Yeah.
Because you have a result.
I can show it everything. You have to give me time to little time, because if I can do this, show only one. Are you the finite volume method?
Is the solution possible because you have found it, or is the solution possible in general?
Okay, no. Finite difference method. I don't have created the finite volume method. It has been, but I have applied finite volume method for this question. But for this question, this is short.
Now, you said, again, I'm coming back. If you want to show that any method is working, you have to show where it's possible. You get something.
Yeah.
Second thing, you want to know if it's accurate.
Right? Yes, that's right.
Now you can we come back to the other details later. Maybe today or tomorrow. But the issue is that you don't touch in the thesis, and you don't touch it in the presentation, in the theory. So, if you have any solution, or any solution, any way, it depends on what you're doing.
Yeah.
How accurate is it?
How accurate?
Yeah.
Yes.
Can we trust your results?
Yes, how we can. Okay. I answer. They have to rely on many different ways, but from one teacher I can say that operational data. Operational data, boundary conditions.
What is operational data?
Yeah.
What makes it long? What is operational data?
Yeah. What was the operational data? They are from the factory that we got that.
So what do you do with it?
By the operational data, it means that how much the kappa number is in the beginning, how much is the end at the end of the derivative. For example, 24. If our result agrees with the operational data, then I can rely to the simulation.
Okay. So how about what's the agreement?
It was, as I told you, it was as we saw it. Then operational data shows the 24 for kappa number at the end of the day. And I guess it's about 24 also. Not exact 24, but it's about 24.
What is the measurement accuracy?
There is not. I explained many times in the here that the production is not stable entirely every day. Today you have 24 kappa number at the end of the digestion. Tomorrow is 24. After 1 hour, 25. After, okay, depend on the trees and the pulse production, there are many things. It's all about but we get something about 24. So we were very satisfied. We could only stimulate the process.
So you mean that's enough for accuracy?
No. There are many things. You said I cannot write them. There are many things.
But now, suppose you have some calculations. Can you show in what way can you check the accuracy or the models? Which models are weak, which models are strong? Which model means which model are more accurate, which models are less accurate?
Yes. I have bubbles here that in a step of to model the power production using the efficient transport, which is very complicated. Very complicated. We use the mass transfer model. We use the mass transfer model. And we use the mass transfer model. This was the best model that I had. I used it for modeling the channels on suitable digester, and I used it for the general production without any phenomena in the digester.
Which parameters you enter to this model? Which parameters?
Which parameters?
You have to leave to the.
That's a very good question. I have to remove all of it. This is a modeling question, so I explain it for you. If you have a mixture, only one phase comes with manual. Different.
You have one question. I have one question was which parameters you enter. Make a list of parameters.
Okay. So only I say volume fraction or another.
For example.
Mass transfer, strain, mass, and transfer for cell mass distribution.
So, for example, let's take divisibility. How do you get it? Where do you get it from?
For mass transfer, I have the calculation for mass transfer to account it, and if you this is a relationship between the production and
production.
Yes, about this is the diffusibility. Okay, this is the diffusibility. If the action is from zero order, then NA is called.
I have thought this different. How big is that?
Yes, I have written it in the thesis. About different diffusivity, I have defined in two mine. I don't have them inside. I think I have them in 9.
Page.
But the math, the most important was M dot EQ.
I must say that because it turns out to be just momentum in water. Or is it that?
Page
74. 74. 74. Yeah. Here.
I can explain for you, but they don't do.
But anyway, you picked up a value which is
I got this.
the same as the diffusion of momentum. The diffusion of momentum which is equal to viscosity. That's what I.
I can explain it. It's the mass transfer rate. I have defined the mass transfer rate.
Point oh, okay. Right. This is page. That's what I did. Which units? Which units?
Aha, the unit is per second.
Don't have it in the nowhere. Don't have any units in the text.
Okay.
Okay, let's go with now we've been jumping a bit around, so we are not in the case. I'll go over to yes, we finally talk here about page 23. You have here section 6.1, monthly schemes. I jump over to
Yes, okay.
you have different parameters there. Material density ratio, Stokes number, volume fraction, and so on.
Yes.
So I try to find Stokes number anyway. You don't use it.
Yes, I use it. Yes, I can.
What is Stokes number first?
Yes, I can explain it. It's the fundamental direction for choosing of the multi-phase model. If I can remove it.
Push the B, and you remove the X.
Very good question. Then, how can we develop
B is not B. Ah, here it is. Oh,
yes.
no projector. No projector. You are going to not have to go back to your own way. Well, you should go there.
when we choose the Eulerian model and we wanted to choose in the Eulerian model, there are all different types of the
Make it simple. Define what is total.
alpha, beta, gamma, alpha, beta, and special number.
What is total? How do you define that? Yes.
Okay.
What is which is what?
Well, this is as you wish. And this is the particle size. This is the particle size.
What is
The diameter of the particle. Diameter of the particle. Density of the particle. This is the density of the particle. This is the ratio of the two times. Now we have tau s. Tau s is LS of the S is this is the length of the, we can consider of the length of the digester, and V is the distance, velocity of the distance, and the other one is for the characteristic sign for the particle.
to do what? What is this type of particles to do what?
When they move inside the digester, when they move inside the digester, the sign of, you mean
why is anything to do with the digestion? You don't have any digestion.
No, I don't know, but here is the viscosity of the, what you mean the collision of the particle.
Now you mix up. It doesn't have anything to do with digestion.
No, only the continuous. This is the
density of what?
This is the density of the particle.
Mm-hmm. Nothing to do with the digestion.
No, but this is now, I mean, I think it's.
So what kind of plan is this?
This is the. I think this is the characteristic sign for the particle, maybe collision of the particle, collision of the particle.
The time it takes, it comes with the name slope. So the time takes the particle to adjust the local flow of the liquid. So it takes, how long it takes the particle to adjust? Now you wrote something about the discussion what number was it? All the time.
I calculated it, I don't know, but it was about 0.4.
You wrote something like this, that the material density ratio, which is 1, indicates the liquid solid.
Yeah.
So, I understand that.
Yes. This one, when it approaches one.
That's the ratio.
Yes, this is the ratio.
The particle with
And the liquid. And when it approaches 0,
what's 1? It's 1. I never said what.
approaches 1. Yes, when it approaches 1, right in the bottom of it. When it approaches 1, Then we have solid and liquid in the model. We have a two-phase. When we wanted to model two-phase fluid, we should consider these variables or parameters. And when it is one, this solid and liquid. This is appropriate for solid and liquid. When it is more than 1,000, we have less than 1,000. Here we have solid and gas. Here we have liquid and gas. It's all the.
Suppose you have now a density. So if you have a how you divide density? Because you divide density just as a basic state. Volume divided by mass by the volume that is occupied. It will be independent of how much you have. If you divide by the whole volume, you can multiply by this alpha. So how? So I still understand how this density gamma equals 1 is indicating a liquid solid flow. It could be. It could be very small.
It is very small, much smaller than the 1,000. Then we have a solid and gas. The possibility. If we want a matrix as a present, this is the solid and gas in the model. So the larger than 1,000, we have and gas.
I don't know.
But we get also, for example, also evaluation of the model.
Okay, another question will hopefully come in here. You were correct that one fraction of this first phase is not just 10%, very close to 1.
Yeah, it's one.
Why do you think this number? That's
how we see the operational data. We know that the volume fraction, they have something that was very important for us when we went while the proportionate, we had observed how the chip moves down, how the fluid moves between these chips, and it was very important for us to understand how to model the chips and liquids in the PhD by PhD modeling. It was very important. And if you look at the digester, who is filled with the chips, only there, the liquid has a very small, very low velocity of the change.
okay, now I have this detailed my picture. Okay. This is in the Basi, 1994, and it shows here alpha. There's a different alpha. Now forget about it. You use the same notation.
Yes, I have used that.
You have, when you go from 10 to minus 9 or 6, minus 3, and you write 1 way coupling, 2 way coupling, particle to particle. That is the first one. That was the story anyway. So three guys showed you get you go to get a test of session, you get -3. It's not 10%, it's 0.1%. I guess you hear.
It's a volume fraction.
It's a volume fraction. It's larger than heat factor. That's 10% tension. That's -3.
1,000. Okay. It's
1.1%.
0.1.
It's okay. And the reason I don't know. The reason is very simple because if you look at the interaction between two particles, particle. And the weight of this particle usually has an effect. There's a weight effect. If you look at a uniform flow, you will see that the flow is uniform here. The flow looks like this is the weight. If you go this to 10 or 15, you see some still in 10 resistance, you have something like 20-25% defect. The value here is larger by about 25% than this one. So it means that you have a weight effect. And if you compute now the volume of this compared to times 10 or 15 diameters, right up with this figure. So it's to get a Euler model, you go down to this, it's enough with 1/10%. 10%. 1/10%.
No, this is not okay. This is not about the Euler. All of them are in the Euler. I didn't say that to go to the Euler, we need to have the volume fraction less than 10%. I did not more than 10%. I said, for some reason, it's telling me only answer what you need. Okay. If we think the Euler, in the Euler model, you can use BPM model, you can use Eulerian, or you can use mixture model. Okay, and it is written, I wrote it from the text from the document, use the graph, that if the volume fraction is very difficult man trying to use the computer, volume fraction is less than 10%, then you can use BPM model. Or BPM model, but it is not checked in the graphics. But it is no problem for us. But you don't use it anyway. No, I didn't use it anyway. I still use the BPM.
You cannot use it. That's why I have this Rashi stuff.
Okay.
Okay. Now that you have used it, you have talked about the picture model, right?
Yes.
You said that in your head, your picture model was not because you have interface. But picture model is very everywhere. That's already a picture model.
Yeah.
So for a picture model, you need a picture positive, right?
Yes.
So how do you graduate it from?
Okay, about the mixture.
Now it's your audio. Which means that
A mixture model.
which one to push here? You have a lot of buttons. Very cool. Vi kommer någonting kort som är Okay, so you have a common positive picture.
Yes, you can. I think so. We have to define a common viscosity for the mixture. But in the mixture model, also you can have two phases, not one phase. So you define the phase.
Two phases.
You define two phases.
That's right. You have a picture. That's the whole name.
Yes, the mixture solid,
but it's not on the interface. Oh. It's
I can explain that. I don't really look here about that. In the mixture model, if I show you only this picture, you can see the difference. Here we have a mixture, okay, but we have different species. Different only species. No phases here. We have no phases here. So we have only mass fraction of any species in the mixture. This is the mixture. We can calculate mass fraction of any species in the mixture. When we have a species transport, they have a mixture here. They have a mixture of different species. Here only we have no phase, only one phase here, one phase. So we can only account the mass fraction of any species, only of this species in the mixture. But when we have two phases here, one phase here, one phase here, but they are only pure material, not mixture. We have volume fraction of this phase, we can account the volume fraction of this phase here, volume fraction of this phase here. But we develop it. We have two phases. One volume fraction of phase 1, volume fraction of phase 2. Okay? But one of them is this. We have a mixture of species, different species. So we can calculate now volume fraction. As you see, we could assign here, this one, here, but not here. Now we have the volume fraction of species I in phase 1. This is phase 1. And volume fraction of phase 2 here. Now, if we have mass transfer between the phases, now one species move from one phase to the other phase from here. So this is the mass transfer, which is the multi-phase model, and they have volume fraction, mass fraction of species in phase 1 and mass fraction of species in phase 2. Now,
What is the visibility for that? Because you see the figure numbers, and that's very important for accuracy, or the result. So how do you pick it up?
so this is this is the mass transfer, not this is not any.
No, that's one transfer. And
This is
here you have the viscosity of the mixture. This is momentum transfer. So how big is this? How big is this?
Yes. When we talk about the diffusivity, this is not about their mass transfer.
I talk about diffusion.
This is mass transfer. Mass transfer. And we can calculate it from the production. It's not this. But diffusivity is something else. It is about the when we have forming of a tissue, we can talk about the diffusivity. If we go to the species transport, only a species transport, then we have the diffusivity, as you say, in the mixture of yes. So diffusivity only uses inside one phase, not from the transfer from one phase to the other phase. This is what I mean. And I calculate.
The way you calculate it, you use the diffusivity, because you don't use volume fluid. Don't use zero.
No.
You don't have, your scales are mixed together. You have, in the momentum equation, you have this interface. And that's included, all the terms included in that. Everything included in that. And that's including also the parameters.
Yeah.
So my question was very simple, how do you take the parameters? For example, this guy, the pieces I had before, and so on. Where do you take it from?
Yes.
How big is that? You have a...
We know that the density of the, for example, the density of the chip, we have this information.
It varies over...
About the mass transfer rate, about the mass transfer, only, about the mass transfer, I use the operational data. It's very easy, but not difficult to calculate it. I had production data. I know how much the production is, how much is the feed, what was the feed, how much was the outlet feed, with different species. had leading here, how much was the leading here, how much was the leading here. So I could very simply account the math answer, right? So it was very easy to account the I calculate.
Well, I'm trying to go back to asking, looking at your presentations, maybe. Oh, maybe so. So, we can go back. Let's wait a little bit. Can you go back to the first one?
Which one?
First.
Is that one? Oh, okay. I have it here. Presentation. Maybe use this one.
This one. Well, anyway. Okay. If you go with this, you have this of the distribution.
Yeah.
You have the major application of different.
Yes.
I come back to the establish the habit mathematical model. So how you convince the audience that you have established the mathematical model?
Yeah. I could compare the model. I could compare the model with the operational data, experimental data, and the boundary condition that when I modeled it, in the first paper, and I modeled only the hydrodynamic fluid, all the muscle and features all the same as we had in the digester, for many inlets and outlets. So my first paper,
And you compare the customer.
I compared it in the first paper. I compared the kappa number in the first paper. I didn't use the chemical reaction. In the second paper and fourth paper, I used the kappa number and modeling the chemical reaction, and I compared the kappa number with the experimental or operational data. It agreed with it. It is 24, about 24, 25 at the outlet. And
What did you conclude about it? We have 1%?
About accuracy, how I can, it is a very good question. I agree with you. I explained this totality, this presentation about the complexity of the half fraction. That we don't know what is going inside. The inlet and outlet, I say that, I confess that. Inlet and outlet result is okay. 100%. Very good. But you never say that distribution inside the digester is, how can I compare it with any comment? Then we cannot go inside the digester. The digester is very huge. We don't have any result, any experimental result from inside the digester to bring it. And we cannot compare it with the batch experiment result also. It's different, absolutely different result.
I agree with you that you cannot go inside. I agree with you that you have no data. That's why I'm asking you talk about prediction of the performance. So if you kind of have no data, you can compare it. How you can predict the performance? And how you make optimization?
Optimization, yes.
But how you can? You don't do it. How do you optimize something that you don't?
Yes, they use. They change, for example, they can use the swing. They change the feed. They can change the feed. If you have,
That's a variation, not optimization. You can vary things. That's right.
yes, you can change, optimize in different ways. Maybe we can change the size of the, for example, the digester. Maybe we want a larger diameter or larger height. Or I don't know, different optimization we can have inside the digester. I didn't get the question to optimize it, but this is a possibility. We establish this code to do this optimization. Any question, most question, something that I have done is to establish a new code than the traditional code that was CSTR and like fluid reaction. Then I wanted to start this modeling. I was absolutely confused. I moved to everywhere to know how could I solve this problem with so many complicated variables and questions and everything. So this is what I can say about the optimization of the
Okay.
so
Then I think I usually ask last question. Usually is what will you do? You talk about the future work. So in the sense that you have a lot of questions, open questions, right? So what will you do? Not what you do in the thesis. What will you do in the future fixing to make them more safe? More accurate, more reliable.
Okay, yes, we have now already. It was it's a very good question. I have to give a very short answer, but I think it was not possible already. They used the CSTR already. It was not possible to model the channeling by CSTR or by PLR. I have discussed it before. I am not into it, but why it cannot. But with the differential analysis, to model the channel on the created phenomena in digester. Now we know how the behavior of the group inside the channel, what happens at the exit feed in the digester. So if there is any solution for it, if there is possible to model it also. So the codes are now established. We can
So this is part of the future working. Everything is fine.
No. We only model the channeling. Now we know what happens inside the digester when the channeling occurs. The production is there. It's before. But I don't have any solution for the channeling right now. But I know that the next step, I have talked about this also to model the pressure. Maybe it's possible, but the channeling is very important. How to solve this problem?
So what is you have a lot of submodels, right? What is the weakest? Which is the weakest one that you think that you should fix?
In the first paper, I paid attention to the fluid dynamics. In the second paper, it comes second, but we forget and forgot about the channeling. It was very important and too important for me because it was about the new method of solution of chemical reaction. It was only this important for me. So improve a new, to develop a new solution.
No, which question I asked you? I asked you what was thesis.
Maybe most part of the important for us. Two answers is the
most important. It's the most important.
What method is
the most problematic one. Okay. Okay, then thank you. I will finish. And thank you.
Well done.
And then we leave the questions to the raised. Yes, not practically thought.
Thank you, William, for this contribution. I think really the digestion of how this is too complex to ever understand completely. But still, maybe the PhD modeling can be one to improve our how to reduce our level of confusion, I think. So maybe it's a question on your thesis. You're focusing on the problems of channeling and hang-up. I would like to ask you, the systems, this is a serious problem in practical operation, and how can it be solved? And if you kind of compare a perfect reactor with a real reactor of modern today, what would you say is the potential for improving?
I don't know if there is any solution for it, because there was another guy that tried to simulate and find the channeling problems, and they got Johan, I don't know what it was, also he was also in the South Africa, and I know that this problem is a general national problem for every new rank also. So I don't know if it's possible to solve the problem when they have so many particles, and sometimes they cut off and painted all the particles, and here they have a challenge in the particles. I don't know if it is possible. But the rest to control is very
how important is it?
It is very important, because when they have even a little channeling in the digester, then this can influence the production. So if this is the outlet, in the outlet you can find some defect in the product. So if not, for example, maybe you have a good pot should have a kappa number 24, but it maybe was only a little channel. Because that we have also small parts of the pot with for example, kappa number 50 or 60 or whatever. That is very bad product. It's combined with the rest of the product. And I was once when I was in the course, and Christopher wanted to show us something, and he took something from the product and showed us this is what we have every day.
Okay, so it's really important from an economic point of view.
Yes, that is very important.
Point of view, but it's not so. It's difficult to quantify. I would like to have some number. The cost of channeling in Swedish houses, 10 billion or something like that, just to motivate more students like that.
It should be very difficult to give any number in this regard, because it happens every day, daily program. It is a daily program, and in this different sense, it may be sometimes maybe channeling causes a shock of in the process. Sometimes no problem, only a little defect product in the process. So it depends on the extent of the extent of the defect in the product.
So do you think that the different manufacturers of equipment are more or less successful in solving that problem, or do they?
I don't think up to now they have solved this problem. They have not solved this problem, and it gets larger and larger. And then they have a larger, when they have a larger reactor. So they have not solved it.
Okay. Yeah, of course, in chemical engineering, we sometimes have this problem in distillation, for instance. If we have a really big distillation column, it may have difficulties of having the same flow in all the parts of the cross-section area, and then we install something called a redistribution plate. We collect all the liquid or the gas and mix them together, and then we put them back in the next section. But maybe that is too dangerous and too expensive to do. But I guess if we have 3 continuous reactors in series, then we have less problems of this type. Obviously, there is a lot of different mechanisms. You have the chemical kinetics of dissolving the liquid, and you have the diffusion of the reaction,